homework assignment, you're really just doing like a single probability. What's the probability that I throw a dart once and it lands into the yellow circle? Or over the whole week, what's the probability that 2 of the 5 contestants win that prize behind the closed doors? We're going to get into, in this section and then later in 10.4, what if there's like more things to consider, whether it be more events or multiple outcomes in a single event. So we're focused today on multiple events, and they can be considered independent or dependent. So here's our definitions for independent and dependent, if you want to jot something down in your notebook. When I think and I try to like consider independent and dependent events, I just think about what independent and dependent means to me in regular daily conversation. I think about a person who's independent. They do things on their own. They don't rely on anyone. That's like a probability of an independent event. What happens in one has nothing to do with another. It's not going to affect it. They're on their own. They stand alone. So the result of one event does not affect the probability of the events that follow. I put in here some keywords. This would be like with replacement. Okay, so for example, let's say I take all of your names and I put them into a hat. And I'm going to draw from the hat and select people to win a prize. Okay. In order for the events, let's say I have 3 prizes, in order for that to be independent, the probability does not change the probability of future events. If I reach into my hat and I pull Alyssa's name, okay, there was like 1 out of 20 that I would get Alyssa. In order to not change the probability for pulling Jack's name, also 1 out of 20, or whatever, how many people we have in here, I would have to put Alyssa's name back in with replacement. If I leave Alyssa's name out because she already won the prize, then what happens that changes the probability of everything after that? It decreases the total outcomes, right? So when I originally pulled for Alyssa's name, I had 20 pieces of paper in there. If I hold Alyssa's name, so down here without replacement, now Jack's probability just went up. 1 out of 19. Okay, so his probability of winning a prize is getting better. Okay. So in a dependent event, the result of one does affect or change the result of the events that follow. Let's see, do we have double names in here? Oh yeah, we've got like Alex and Alex. Okay. So, Alex, it depends like whether if I'm just putting in one Alex name or I'm putting in their 2 separate names, but they will both win, okay, if I pulled their name, so they have better probability. Okay. In the case of without replacement, there would always be 2 Alexes in the hat, but if I hold that, with replacement, there would always be 2 Alexes. If I hold the Alex outside, then not only does the total outcomes change, but so would their favorable outcomes. So sometimes it changes both your favorable and your total, and then sometimes it just changes your total. So there's 3 little scenarios right below. Would you read those out with your pods and try to decide what you think? Independent or dependent? Does the result of one event, the first event, change the probability for your second event or choice? Right, or you do those with your group. first two should be pretty clear, right? That's the whole piece of like with replacement or without replacement. So you draw a queen, you replace the card that's independent. And then if you're doing some card work and you draw a king and you keep it, and then you draw another face card, that would be dependent, because if there's one less king, there's one less face card, so that would change our favorable outcome, and there's one less card in the deck, so that also changes our total outcome. What did our group say for a month is selected at random, a day of the month is selected at random? Is that independent or dependent? Maddie?
You said it was dependent.
And your reasoning?
Because different months have different amounts of days, so like you couldn't have like February and then choose like a 30.
Argument is sound, right? Good thing we're in February, so we're thinking about that. And maybe even the year matters, because some Februaries you could pick 29 and some you can't. Okay? So, yeah, I would say that's dependent, because you wouldn't be able to choose certain days in months that have less. Okay? Excellent. Okay, here are the formulas. Make sure you get these down in your notebooks. Okay, for this is independent. Sorry, it's hard to see. For independent events, if you want to find the probability of A and B, and I put a little then below it, so like when we do probability, we use the word and, but what we mean in this and is and then. So like we're doing multiple events, because later on in the chapter we're going to have an and that means at the same time. And so you have to be thoughtful about which kind of and you want, and then or at the same time. Okay. So if you want the probability of A and then B, you take the probability of A, oh, my little times got stuck up there, times the probability of B. So in this case, and this will be helpful later on, and means multiply your probabilities. Okay, later we're going to have the word or. The probability of A or B's, and those are not going to be multiplier probabilities, those are going to be add your probabilities. Okay, later in the chapter. So right now, and means multiply. Okay. Now, for dependent events, you technically have the same formula. You just multiply your probabilities. Probability of A times the probability of the second event, but it has a new notation. So it looks almost exactly the same, probability of A times the probability of B, but there's this extra stuff. Okay. So this reads the probability of B given A has already occurred. And the reason we use that notation for a dependent event is because B depends on A. Its probability changes when A happens. So you just have to be thoughtful about like what is that probability of B if A already happened. You know, if that's like doing the card problems that you listed as independent and dependent, the dependent one, you would have to lower the total number of cards, and in that king, you would lower the number of face cards on the next probability. So you just make the adjustment, okay, to the second probability. And that's all there is. Can't remember. Do I have a conditional probability on there? Oh, it's not there yet. Okay. I just want to make sure that I get it. Okay. Talk to your group. Answer the first problem.
Like I did like a 5. Like you spend the weekend, you're trying to find that first 2 are
And then let's just
okay.
you have to do 2 events, pulling the bills, and you want to get $100 each time.
Oh wait.
Here's how I. So just go by the first chance. Go by the second chance. So what's the first chance of getting $100? $1 $100 will be 1/5 chance. And then do the next one. So provided that you got the outcome that you
Oh,
want,
I see.
what's the next one? Now there's a 4 out of 24 chance. So then you multiply 1/5 by 1/6. So then that's a 1 out of 30 chance.
Okay, so I think I'm hearing some really good conversations about that we're doing a $100 bill and then another $100 bill. So we have 2 events. We're pulling 2 bills. Probability of pulling a $100 bill. There are 5 of them, and there are how many bills? 25 bills total. So 5 over 25, and I saw some groups reduce that to 1/5. Either is fine. Okay, and then so we're going to multiply because and means multiply. If you keep that bill, what's the probability you get another $100 bill? 4 out of 24, or some people reduced it to 1/6. Okay. It doesn't matter whether you use the larger numbers or the smaller numbers. You know, if you want to leave your answer as a fraction, then it's easier to do 1/5 times 1/6 and get 1/30. It's already reduced. Here we'd have to reduce it. You can do it in your calculator, 5 over 25 times 4 over 24, and what does that come out to be? 0.033 repeating. Okay. Between 0 and 1, it's not negative, it's not more than 1, so I'm feeling pretty good. As a percent, that's 3.3%. So I'm not really a great chance of getting 2 $100 bills, but I will give it a go. Okay. I'd be okay with that. And just in context of like our formula we just wrote down, this right here is the probability of getting 100. Right? It's the first thing you do. There's 25 bills. That's the probability of 100. And technically, this probability right here is the probability of getting 100 given that you already pulled the 100 without replacement. So if you wanted to write out those probability notations, they're there. But mostly the thing that you need to know from today is if you're doing one event and then another event, you should multiply probabilities. And that is the key. Okay. I think, how well do you guys know cards? Should we talk about this one so we kind of like run? I'll talk about the deck of cards. This might be helpful because the book might have some card problems for you. Okay, find the probability of drawing 2 cards from a standard 52 card deck, selecting a heart and a red card. So I'm going to talk about the 52 card deck. Okay, 26 of the cards are black and 26 of the cards are red. So it's half and half by color. And there are 4 suits, hearts, diamonds, clubs, spades. So you have 13 hearts, 13 diamonds, 13 spades, and 13 clubs. Okay, 13 in each suit because you just divide 52 by 4. And let's see. Then within the suits you have like 13 different kinds. Ace, 2, 3, 4, all the way to 10, Jack, Queen, King. So you have 4 of a kind. Okay. And a kind is like an ace, a 2, a 3, a jack. Okay, so you always know you have 4 jacks, 4 queens, 4 kings, because you got to have one in every suit. Okay. And then a lot of times there's questions about face cards. So the face cards are the jacks, queens, and kings. And you have 4 of each of those kinds. So you have 4 jacks, 4 queens, 4 kings. And that would be a total of 12 face cards. Let's see. Does that make sense? Am I missing anything I should be telling you about the cards? Can't think of it right now. Some of us are going to be better at card problems because we play cards. Some of us don't know the different cards very well, so then these problems feel really hard. Okay. But you can always ask me about the deck, but I won't tell you how to do the problem. But I'll tell you about the deck of cards. Okay. So then if we were doing like the probability of selecting a heart and then a red card with replacement, the probability of a heart and a red, well, the probability of getting a heart is 13 out of 52 or 1/4. And the probability of getting a red card is 26 out of 52, and we did it with replacement, so it would be 26 out of 52 or 1/2. Okay, whatever that may be. And then in part B, the probability of a heart and a red card, given that you've already pulled the heart, think about what would change. Well, the probability of the heart will still be 13 out of 52, but if you pull a heart is red. So now you have 1 less card in the deck and you have 1 less red card. So you could multiply those together. Okay, I want to make sure I get to conditional probability. So conditional probability. This is maybe the first thing of probability that maybe you've never really named. I'm not sure if they do conditional probability at all. So this is actually giving a name to that special notation I had on dependent events. It's the probability that event B occurs, given that event A has already occurred, and the events are dependent. So it's that changed probability. It's conditional because there's a condition. If this happens, then my probability is that. So it exists when they're dependent. You know, if your friend is having a party this weekend and someone you like is going to be there, you might be more likely to go to the party. Or someone you don't like is going to be there, you may be less likely to go to the party. So whether you're going to go or not might depend on who's going to be there. And that would be a conditional probability. So that's that special notation. I usually write it as the probability of B given A because it's the second probability, okay, depending on the first one. But like when you name things as like events A, B, or C, I mean, you could have any pairing of 2 letters there. Okay.
Is the line in the middle like a division sign?
Yep.
Or, okay.
Oh, no, between the B and the A or right
Yeah,
there?
Between the B and the A.
No, it's just it means given. B given A. It's just because mathematicians are lazy and don't want to write it out. So we made a notation to mean B given to A has already occurred, so we don't have to write it. And then there's a formula for this, but I'm going to be real honest. This is dependent events, right? So the probability for A and then B is equal to the probability of A times the probability of B when they're dependent, given that A has already occurred. And all I'm saying is we're interested in this conditional probability right here. So divide by probability of A. So I don't know if you want to have to memorize that formula or whether you see it as just the dependent events and you could solve for whichever probability you want to. Okay, it is the same formula. Okay, now sometimes this, like either setting up the black equation that I wrote and then like doing the division or knowing this formula can be super helpful when you're given probabilities of events A and B and event A and you want to find the conditional probability. That's the way to go. Okay, but I think I have an example where we're going to do eventually down at the bottom we've got a conditional probability, but we don't even need that formula. So this one's going to go fast. Okay. Let's see. The computer lab has 10 computers. Some have CD drives. Some have DVD drives. Man, this is an old question. Okay. You guys are like, what? Some are new and some are used. A student picks a computer at random. Use the table to find the probability. So the probability that the computer is new, there are 7 of them, and there are 10 total computers. So 7 out of 10. 0.7. Okay. Probability that the computer has a CD drive. There are 6 of them. There are 10 computers. Probability that the student picks one, it's new and it has a CD drive. So it's new and it has a CD. There are only 4 of them, so I'm not using the totals. That would be 4 out of 10. And then notice the last one is going to be a conditional probability. The probability we pick a new computer given that it has a CD drive. So new computer given that it has a CD, that means you know it has a CD drive. So you're not choosing from 10 computers, you're choosing from 6. So the total you would choose from is 6, given that it has a CD drive. It absolutely does. And then how many of those could be new? 4. Oh, I suppose I should be reducing some of these. 2/5, 3/5, and this one will be 2/3. So you have to be really careful when you're reading your problems and make sure that you account for any like given information. If you have a table or you have some knowledge about like boys versus girls and it says what's the probability that they voted yes given that it was a male respondent, then you only choose from the males. Okay, so that does the conditional probability for you. Technically this is the probability of A and B, so new and a CD, divided by the probability of A, the probability that it's new, that would be the probability that it's a CD. So it would be 4 out of 6 divided by 6 out of 10, which then the 10s cancel, and you get 4 out of 6. I'm going to skip. Is there one more? Okay, so this one is, like, you got to be really careful when you read the question. Okay, because the last one I had it all set up for you in probability notation. Okay, I get a lot of people get these wrong on quizzes and tests because they don't read. So quality control inspects for defective parts. Here's this little table for what they found. Find the probability that a defective part passes. So what do you know about the part? It's defective. So you don't want to do all the parts. You only want to look at the defective parts, which the total is 29. Given that it's defective, what's the probability that it passes? The answer would be 5. Okay. I'm going to get a lot of people who would add up everything and do 5 out of the total. But I don't care about the total. I care about the defective parts. Okay. Find the probability that a non-defective part passes. Non-defective passes is 208. What's my total? 217. So you have to read, okay? Those things are going to be your givens. Okay? So it means don't do it out of all the defective and non-defective together. Do it only out of the 2 that you know. And then real quick, the last one. This is the one where, like, actually you would need the formula. Because I'm given percentages, so I know the probabilities. At a clothing store, 75% of people buy pants. So I'm going to say 0.75. Only 20% buy pants and a belt. 0.2. What's the probability that a customer who buys pants also buys a belt? So the probability of buying a belt given that they bought pants. So you take 0.2 divided by 0.75. Okay, and you can play around with that one if you want to look up the formula for conditional probability. Probability of A and B divided by the probability of A. Or if you want to set it up as like the probability of A and B equals the probability of A times this conditional probability and then divide by A. Okay, but you get the same answer either way. Okay, so on Tuesday when I see you again, I'll want to see both homework assignments, so make sure you've worked on them.